going to start. So, pleasure to introduce Michele Triestino, who's going to talk to us about space in the water. He's on the line.
This is actions on the line.
This is actions. Sorry.
Yeah. So I'm going to say part of a project. A small part of a project we started during COVID with Brum, Nicolas Macedon, Cristobal, who is going to speak more about other parts of this project. So before I get to really the point of our discussion, what we're interested in now, I will spend some time explaining a construction from which all of this started. Is the first constructions of simple finitely generated orderable groups. Okay. So the first examples were given by James Hyde and Yash Loda. And there was like a generalization of their construction made by Nicolas Macedon and myself. So before I define these examples, let me recall really one of my favorite groups, which is the building block for these groups, which is functional group F. So what is this? It's a group of piecewise linear homomorphism of the unit interval 0, 1. And simply says the set of all homomorphism of the unit interval locally of the form T goes to the power kt plus T over tq, so dyadic affine transformation locally, and breakpoints, so points where the derivative is not defined, you want them to be contained in the set of dyadic rationals. And let me take another color. If I replace the unit interval by some other interval I get another group called F sub I, and this is isomorphic to F whenever I is a dyadic interval, so the endpoints are dyadic rationals. Okay, so this group is a quite remarkable group. Everybody knows it's, but sometimes define this group to find examples of finitely generated and finitely presented group, simple groups. This group is not simple, it is finitely generated and finitely presented, but its derived subgroup is simple, okay, but not finitely generated. So this is one of the building blocks. The idea is that to replace the space where you make your group act, so you still are interested in groups of piecewise linear homomorphism of some space. We want it to be compact to get simplicity. And for this, we do the following thing. So you take X, a compact space, totally disconnected. It's called a stone space. So compact, totally disconnected. So you can think, for instance, of a Cantor set, and you consider a homomorphism of your space X. So when you have a space, a homomorphism, you can build another compact space, which is the mapping torus. So I call this Y, which depends on the map phi. So this is X cross the real line where you identify a point X T with the image according to X, and you go back in time by 1. So in other terms, you make X cross the unit interval 0, 1, you identify the floor with the bottom using the dynamics. This is standard mapping torus. And so I'm writing things like this because then you have a natural projection of X cross R onto this mapping torus. And this allows us to define nice charts on this space. What are the nice charts for us? We consider U inside X a closed subset, and I inside R dyadic interval. And so we require that such that the projection of U cross I inside Y is an embedding. So somehow you have your space with this one unified with this. What you want is that you want to look at tiny boxes with U cross I, but sometimes things go like this, and then you have to spread things around using the dynamics. But as long as the images are embedded, that's fine. This will be our box. And define box groups, box Thompson groups. And define the box group F sub U cross I is the collection of elements which act as Fi in the vertical direction, F sub I. So this is the set of collection of elements H from say U cross I to U cross I of the form H of X T. This is just X. You do nothing on the first coordinate, and then you use some map element F of T, where F is a fixed element of F sub I. So this means that you choose your favorite. So this is your box, and you use an element of F sub I, always the same one, to move things in the vertical direction. So these are elements which are supported only on U cross I, and you extend them as the identity outside your box, outside your chart. And so now this is the group. What you define as a group is what we call T phi. This is the group generated by all the box Thompson group. It's like solenoidal Thompson group. What are the results? As you can prove, I read it with Nicolas Mathibon, is that first thing, T phi is finitely generated if and only if essentially X phi is a subshift. It's conjugate to a subshift. Let me say it's a subshift for simplicity. Second thing is that T phi is simple. The subshift is it's a subset, sorry, it's X inside A to the power Z, which is closed and shift invariant. And you take as phi the restriction of the shift map to your invariant set X. That's a subshift.
What is A?
A is a finite alphabet. And you have a characterization of simplicity for these groups. But simple is equivalent to the fact that this dynamical system is minimal. Okay, so any orbit is dense. So if you take a minimal subshift, then you get a finitely generated simple group. And why are these groups left orderable? Well, you have to put some assumption for this on the dynamics of phi. Is that so? These groups are naturally subgroups of the homomorphism of the suspension space Y. And by definition, as I'm defining them with local support, they're isotopic to the identity. And you see, you have this action on this laminated space. As they are isotopic to the identity, they are preserving any lift. So when you consider one lift, when you follow it, one lift, the group will act on that leaf. And this leaf is, if it isn't, if it is not coming from a periodic orbit of pi, this is a copy of the real line inside your quantum space. And so in this way, you get an action on the line of your group T5. And if you have many infinite orbits, so for instance, if any orbit is dense, the action of such a leaf is faithful. So you get the faithful action on the real line, so the group is left orderable. The nice thing that I want to discuss more is that we don't only get an action on the line for this group, we get really several actions at the same time on the line, because if you choose another leaf, then you get a different action on the line on this space. Okay. So the question that we were asking at the time, does any action of such a group on the line come from an action on a leaf? Am I seeing all possible actions on the line from the action on these mapping turns? So does any action of T5 come from an action on R, action on a leaf? I will be more precise on that. I will state one result that goes in this direction. But before doing that, I have to explain to you which is the difference with the construction of Iden-Loda.
Sorry, Michele.
Yes.
Where is it? What part of the theorem relies on this thing being totally disconnected? Or why do I need to totally disconnect it? Why do I need X to be totally disconnected? What's important here?
So the point is that we are using, you see, a subshift.
Oh, okay.
I mean, at the end of the day, we are using the fact that the cylinders generate the topology of the space. Somehow that's the basic point.
Okay. Thank you.
Also to define things, you know, when I have open subset, and so I have boxes, and they all match up together to define the homomorphism of the space, because if you don't have something totally disconnected, you don't know how to match different boxes together. There will be a discontinuity for the action. So let me explain the difference with the construction by Iden-Loda. They define the groups in this way, but it is not difficult to see that this kind of construction recovers their construction. So for this, I will consider special class of homomorphism of stone space that I call freely reversible. So reversible means that you have an involution that conjugates your map to its inverse. We have an involution sigma conjugating a phi to the inverse. And this is for the reversible part, and freely is this condition. When I look at the image of a point X, I don't want it to be either X or phi of X. This looks a bit technical, but if I have such a thing, then now I can construct what I call a mapping line battle. So this, instead of taking a quotient by the action of Z, I take a quotient by the action of the infinite dihedral group. So if I want to do this correctly,
Michele, that is for all, or is that this?
for any X. For any X, I want this. Okay. And so what you define a mapping test battle, which is you take Y and you quotient under the relation that you identify X T with sigma X minus T. And I call this Z. This is my mapping test battle. Okay. And the way, and you can do the same thing. So you define T phi sigma, which is the group generated by the box groups inside the group of homomorphism as adapted to the identity of this mapping time battle Z. So now you have to, but you have to take care that the boxes now you really want them to be embedded into the mapping class battle. So you have a restriction now on the charts. So somehow, if you take a chart in Z, they lead to two disjoint charts inside Y. And basically, if you choose some phi and sigma correctly, you recover the examples of infinite finitely generated simple irrefutable groups by Ivan-Loda in this way. They say come from this construction. And let me give you another way of seeing that. It's just nothing but lifting the action. So as everything is isotopic to the identity, you can lift it to the double cover. And so what you want is you can see also this thing as inside this is isomorphic because it lifts to the centralizer of the map sigma at of x t sigma x minus t in T of phi. So this is naturally a subgroup of T of phi as you just lift it to the mapping torus. If you want, they commute with this involution of the space. And so just a word on the terminology. So the point we call this map freely reversible is that if this condition is satisfied, this means exactly that this involution has no fixed point on the mapping torus. That's why we call this freely. And then you can ask the same question for these groups, T phi sigma. Well, yes.
I don't understand the difference between T phi and T phi sigma.
So T phi sigma is the one defined as homomorphism of the mapping plane battle. So it is generated only by. So this is not the same thing. I'm using the same notation, but now you have really to look this group. So like the group generated by the images of these groups inside the group of homomorphism of Z. It's better to think of them in this way. It's the centralizer of this involution. So we can ask the same question: does any action on the line of this group come from this construction? We are not able to solve this question. There are some technical problems, and so we change the group. We change the group. We make a slightly different definition of the group. Instead of T phi like that, we define like T phi sigma. Okay. And we define also T phi like this. And what are these groups that we change as we replace this with some curly S? And then you do the same construction. And what is this? Curly S. This is basically you add you can specify the singular point for these maps. You allow singularities which are accumulated by standard breakpoints. It's still a finitely generated group, but what you get with this construction is that now these groups are perfect. So what we want is that the group of germs of when you look at germs at 0, you get the perfect group, which is not the case for the group F, because the group of germs is basically the derivative at the point 0, which is isomorphic, and this gives a group which is isomorphic to Z. And so we complexify this a bit to have germs which are which give a finitely generated perfect group. And so the result is that for this group T phi sigma, under some condition on the dynamics, we're able to answer this question positively. Okay, so now it's time to please. I don't want to give the precise definition of this curly F. It's not very important. Yeah, yeah. The white chalks, good. So this is the theorem. So assume that x phi sigma is fully reversible. The free reversible subshift, and assume periodic orbits for the collection of all phi periodic orbits in X as empty interior. This is necessarily satisfied when the action is meaningless because you have no periodic orbit. But so this allows you to consider more general subshifts. Then, if rho, and they call, let me call from P phi sigma into the group of all of the line is an action without global fixed points. Let me abbreviate this by saying irreducible. Then there exists a lift inside Y such that and a non-decreasing monotone map H from R L, so that so what you want is that you conjugate the two actions. So H opposed with rho of G is the same as element G. I can ask the application of H for any G in the group. Okay, so it means that any reducible action is semi-conjugate to an action that comes from the section on the left. Now, this is the result. I'm not going to discuss the proof of the result. The paper has almost been written. Just rewriting the introduction over and over and see how we can push this kind of results. One of the quotes just said the baby, so things are getting slow. But I want to take this as an excuse to discuss this more general program that we have to describe the space of actions of a group on the line. So somehow what you get from this result is that the mapping torus is a moduli space for action on the real line of this group. And it's something really general that exists for any finitely generated group.
What's the ordering that little L there that makes it monotone?
Sorry?
Yeah,
Yeah.
the L, what's the ordering?
It's the order given by the direction of the flow. So you can always, I'm inside Y. Y is the mapping torus, so you have an orientation. It's not the Klein battle. And so here you really have to think about the action coming from seeing it as a group of homomorphisms of Y, not inside Z. So for the same reasons, this way you really have an orientation. So, by the way, something that Andres mentioned last week is that for these groups, T phi and T phi sigma, we were able to prove with Nicolas Mattebon and also separately Andres, Cristobal, James Hyde, and Yash Loda, that any action on the circle of this group has a global fixed point. And somehow this kind of result is saying more because it also gives you this result as a corollary for this kind of groups. You don't see action from the circle. And you have an action on the circle only if you have a closed leaf in the mapping torus Okay. Yeah, by the way, when this is a closed lift, this is an action on the circle. So this is not a line. Non-decreasing means, okay, you lift and you have something, which you give a semi-conjugacy. Okay, so let me give the really general setting, which is quite abstract. So we're interested, as you see, in the notion of semi-conjugacy, understanding actions up to semi-conjugacy. And this is a pretty bad relation, equivalent relation. So usually semi-conjugacy between two actions. So if you have two actions, row 1, row 2, from a group G into you plot order preserving homomorphism of the real line are irreducible. Okay. We say that row 1 is semi-conjugate to row 2 if, so this is an old-fashioned definition, but I'm using this. There exists another action of your group G and non-decreasing continuous maps H1, H2 from R to R, such that the same thing holds. HI composed with row I of G is equal to row of G composed with HI for any I 1 and 2. Okay. Okay. So this is the old definition of semi-conjugacy. With this definition, you don't. This is not an equivalence relation, but you can take the equivalence relation generated by this relation, and consider a different kind of relation. I put a P here. This is for pointed, and pointed means that you want HI of 0 to be equal to 0. I'm not considering any kind of semi-conjugacy, only considering semi-conjugacy that take your marked point to 0 to 0. Okay. So you have to think about marked semi-conjugacy classes. Somehow, if you think of your mapping torus, this is the same as choosing one base point, one marked point on the left. And the reason for doing that is that there's something great going on. The quotient of all irreducible actions, when you look, so I call rep G R is this is the space of reducible actions. And this is a topological space when you consider the compact open topology on homeoplast of R. So for instance, if the group is finitely generated, you have your finite set of generators, and you say the two actions are closed if the images of the generators are closed in relation to a really large compact subset of the real line. Okay. And because of this, because you have to consider compact subset of the real line, you have actually that the space of reducible action is neither open nor closed, the space of all actions of your group on the line. So you consider the induced topology on this space. And there is a result, basically to Deroin, is that when you look at the quotient, the collection of pointed semi-conjugacy classes of reducible actions is actually homeomorphic D of G, which is a compact subset subspace, the space of all the reducible actions.
Wait, what are you quotienting for?
Well, taking all the pointed semi-conjugacy classes of actions on the real line, and taking a quotient.
So that's like that's weaker than conjugation.
Yeah, there is a yes, there is a smaller quotient which is considering also semi-conjugacy classes. But I prefer to use this, take this quotient, because you have this great result that you can actually realize this quotient inside the space of reducible actions as a compact subspace. This is what you have. You have a natural quotient from the space of reducible action to this quotient space. And the theorem of Deroin is telling you that you have a compact section of this quotient map.
So this you think is the meaningful notion of character, like modular space of representation.
Yes, this is modular space of reducible actions. Yeah, with mark point. Marked reducible action somehow. And so this marking, now you can actually, you have a marking, and this is defining a dynamics on the space, because this space is invariant under topological flow phi t, which is taking reducible action rho, and you conjugate it, this, using the translation by t. Standard rotation of the real line. So basically you are moving the base point for your action. And this Deroin space is, we call this the Deroin space. It's invariant. So you have a compact space preserved by this flow. You also have a free involution, we call iota hat, which come from the conjugacy, where this is like the order reversing isometry. If you have an action, you have also the action the line with reverse orientation. And so you see now you have like this compact space with this translation flow phi t and this free involution. Okay. And this is what is giving the this is our Deroin space, is modular space which comes with a translation flow. And what is nice is also that all phi t orbits correspond exactly to semi-conjugacy classes. If you have two actions which are semi-conjugate, then they are in the same phi t orbit. So somehow, if you take this space and you quotient it with, you look at the phi t orbit space, is exactly the space of semi-conjugacy classes of irreducible actions. So, but this quotient can be bad, pretty ugly. When you have the orbit space of a flow in a topological space, this can be something bad. And so the theorem that we have here, this is giving exactly that y with, say, phi t, which is a mapping torus, so there is a flow in the vertical direction, and there was this free involution. This is actually isomorphic to the Deroin space of the group. Homomorphic, please. Topologically. So what you see here, this is something that you can define for any group, and here we have a concrete realization of this space. And there is a theorem that you have to prove, is that so for defining this, Deroin has to make many choices. So the first choice is that he has to take a finite generating set for the group, and then he has to consider a symmetric rounded walk on the group to define the space. So it depends on a finitely supported symmetric probability measure on the group. And you can prove that actually this space is canonically defined. So if you have two distinct compact subspaces that are realizing this quotient, they're actually homomorphic by a homomorphism that is taking one orbit to another orbit. Really defined doesn't depend on the choices. I mean, up to homomorphism. and want to spend the main time I have to, well, first give other example of Deroin spaces for the easiest case.
What do you mean by canonically defined?
If I have, so if I have a compact section of this quotient map, then they are actually homomorphic. By homomorphism, that is taking any phi orbit to any phi orbit. So as a topological space with a flow, there's only one thing up to homomorphism.
Okay.
Let's take examples. So these are the examples of abelian groups, or more generally, groups without free sub-semigroups, such as groups of intermediate curves. In this case, we learned last week that any left order on the group is conradian, and you have a conradian order, then you have a Conrad homomorphism defined on your group. Which what is this doing? This is semi-conjugating the action of G, the dynamical realization of your order, to an action on the line by translations. It's semi-conjugate, the dynamical realization of the order to an action by translations. So this is telling that any action of an abelian group, homogeneous group without free sub-semigroups, is semi-conjugate to an action by translations. And so an action by translation is just determined by a morphism of your group into R. And so this means that if I want to describe the Deroin space of my group, I have to look at all morphism from G to R. So in fancy notation, this is H1 for your group. But you can, it's not exactly this because this is not compact. So the point is that you have to fix a scale. So if you, you have to quotient by multiplication by some fixed scalar positive number. Okay. If you have a translation by 1 or translation by 2, they are semi-conjugate. They are conjugate one to the other by multiplication by 2, 1 Okay. And so this is a sphere. So this is a sphere of dimension B1 of G minus 1.
So you're removing 0.
Yeah, sorry, yeah, no trigger. With reducible actions, yes. And so this is a compact space. What is the flow on the space? So these are actions by translations. And the flow is taking an action conjugated by a translation. So translations commute. So this is a sphere which is fixed by the dynamics. And the involution is just the antipodal map. So in general, if you have a general finitely generated group, you always find a sphere which is fixed by the flow inside the Deroin space, because you have to consider all possible actions of abelian quotients of your group. Okay. So in our case, you were perfect that there is no sphere, no fixed point for your translation flow. But in general, when you take a general group, you will have no trivial abelianization, so you will see a fixed sphere for the dynamics. For more examples, would be later today in Cristobal's talk. Okay. What I want to explain now is why this shape is canonically defined. This comes from ordered structures on your group. So when you consider actions up to semi-conjugacy, it's not really left orders that are the good notion. What you have to consider, so the point is that there can be large stabilizers for the actions. You could have no free orbit for the action. So the relevant notion here is the notion of pre-order. The pre-order is like an order, but there are things that are equivalent to the identity. What is a left pre-order? It's a decomposition. The left pre-order, so that we call this less than or equal to. And what are this? Here's a semigroup of positive elements. This is a subgroup, and these are the elements which are comparable to the identity. Okay, so H is the set of elements in your group such that G is comparable to the identity. That's why it's a pre-order elements that satisfy this. And what you want is that, okay, this is a semigroup, and the extra property that you want is that you want something which is non-trivial. And the other condition is that when you multiply a positive element with an element which is comparable to the identity, then you get still a positive element. That's a pre-order. And so if we pre-order, then you consider the space of less pre-order on G, and this is naturally a subset of this Cantor space. And so, and it is closed, so it is compact. And when you have an action on a group of G on the real line, if you take a base point, you automatically get a left pre-order by looking at where the point is moved. If it is moved to the right or to the left, and if it is fixed, you get something which is comparable to the identity. That's the way you pass from left pre-orders to actions on the line. So the other way around. But then we have to introduce something which is looks like the pointed semi-conjugacy. And semi-conjugacy here is something that what you want to consider. You will want to say that two orders correspond to the same semi-conjugacy class if more or less if positive elements for one pre-order are the same for positive elements for the other pre-order. So that's the definition. Okay, two pre-orders. We do like this, probably, I don't know if this is the right terminology. So one pre-order is dominating another one. Let me write something like, which way? Yes, like this. That's a notation. If when you look at the identity map, you want this to be order preserving. And this is equivalent to asking that you have more positive elements here. And also what you want is that, so if you look at H for the largest one, so this is smaller, and this one is convex, the convex subgroup for the other pre-order, and you have that. So this thing is obtained by taking the positive elements for this pre-order and removing the elements that you have. Yes. Yes.
Are you also getting only non-trivial?
It's not trivial. Yes. It's like you for irreducible actions. If trivial pre-order is something that you corresponds to an action, to the trivial action.
But you have a compact set, including the trivial.
You see that something. You said something. Which is compact. We proved this. The group has to be finitely generated, yes. Yes. Yes, finitely generated, yes. Always finitely generated. Finitely generated, that's fine. This is finitely generated because you always have a maximal convex subgroup given a pre-order. And so basically what you have is that in any dominating class, you have like a maximal element, the one that's dominating everything, which is the one that corresponds to the largest convex subgroup. Okay, so there's always a maximal element, so that H is like the largest convex subgroup. The way to formalize this, but it's basically the same as asking that an action when you look at semi-conjugacy classes, there's always a best choice for your representative, which is actions which are minimal, and this is doing the job. Okay, and so then you have to prove. So this is one proposition. Time. Is that when you consider the quotient under this domination, this is Hausdorff. This doesn't come for free and compact. And then the theorem is that actually the Deroin space is homomorphic to this quotient. So this is something which is intrinsically defined by the algebraic properties of the group. It doesn't depend on any other choice. The problem is that with this point of view, it's difficult to see this translation flow. Okay. So this homomorphism is only with some of topological spaces. And then you work a bit more, and you can also say that if I have two there are spaces that are actually homomorphic by homomorphism that takes orbits to orbits. And moreover, we use this identification to say that when I look at the quotient map, so you take an action and you send it to the unity representative of the pointed semi-conjugacy class, this action is actually a continuous retraction of the space which preserves the pointed semi-conjugacy class. And this is great because this means that if we understand the topology of the Deroin space and its dynamics, we are able to say interesting things about the space of all irreducible actions. I now have time to write a clear statement, but let me say for the group curly T phi sigma, this allows to prove that choose phi minimal subshift, then you have that any semi-conjugacy class is dense in the space of irreducible actions. But if you look at path connected components of a reducible representation, these are exactly the semi-conjugacy classes. It's like the same topological picture that you have for the suspension space. It is a connected space, but the path components are exactly the leaves. So we are able to say the same for the space of semi-conjugacy classes inside the space of reducible representation. Okay, there would be more this afternoon with Cristobal. Thank you.
Are there any questions from Michele?
Yeah. Okay, first of all, what about the circle?
Okay, so for the circle, so semi-conjugacy classes are detected by the bounded order class, as we learned last week.
So that's
okay. So so you don't need to consider pointed semi-conjugacy classes because you have already a nice classifying space, nice moduli space.
Okay, cool. Okay. What about the structure of this space? So if I in the finite dimensional represent, like in a compact Lie group, right? This representation space is before quotienting by conjugation is a manifold, and then you can what's
fair. In the case of but these are certainly not manifolds. You get this mapping torus.
Yeah.
In the case of the circle, so there was this really great result by Mann and Wolf that they tried to describe some path connected components of the space of representation of surface groups into the group of homomorphism of the circle. Okay. So they are able to say something, but they are not able to describe everything of the space. So in general, it's a really difficult problem to describe modular space like that for representation.
So there is no, like, it's not an, I mean, this is not a quotient by a group action. That's not an orbital.
It's like, so in the case of representation to the group of homomorphism of the circle, Man and Wolf explain that you can see it as a GIT quotient for the action of biconjugacy of your group.
Ah, wonderful.
Okay.
But while for the real line,
For the real line, the point is that it's better to consider this pointed semi-conjugacy because the compact operator topology is bad. So this is a good replacement for it. Also, we are restricting the attention to reducible actions. There's something you don't do when you consider actions on the circle.
yeah, I mean, yeah, reducible actions.
And so, topology of a reducible action, I was saying the compact operator topology is bad.
Yeah, I mean, that makes sense.
Okay.
And
so that's a good modular space. It really,
yeah, it's compact too. But this semi-conjugacy is stronger than conjugation, right?
Yeah.
So the space is compact, but maybe when I push it I identify by conjugation, I get a larger space.
you don't get out of space because limit. You can take a semi-conjugate and approximate it by a sequence of semi-conjugate is approximated by a sequence of conjugacies.
Oh, that's I see. But for the circle, I can think about this as a GIT quotient.
Yes.
That's one.
Yes.
Okay, thanks. But do I have compactness for the circle?
No. But you can define the null space also for actions on the circle.
All right, if there are no more questions, let's thank you, Kelly, again.